Hello everyone, welcome back to Fluid Mechanics homework number 2. This will be part A. Part A is broken up into two problem statements, so let's look at the first one. So the first problem statement states to derive an expression for the vertical force on the spherical end cap of a horizontal capsule with cross-sectional radius r that is half filled with fluid. So I'm going to draw our capsule here. So here's one end cap. And here's the other end cap, and it's half filled with fluid. And we're trying to find the vertical force acting on the end cap of our horizontal capsule. So the vertical force will actually, if we're taking upward as y and horizontal as x, the vertical force, Fy, will be equal to the weight of the fluid in this section of the end cap. So how do we get the weight of the fluid? So our Fy is going to be equal to the volume, which will be for a sphere, it's 4/3 pi r cubed, times the section that we're looking at, which is a quarter of a sphere, times the density of the fluid, times g. And this is the vertical force on the spherical end cap of a horizontal capsule with cross-sectional radius r that is half filled with fluid. So I'm going to label this part as part 2. And I'm also going to redraw our capsule. So here we have our capsule again. And we know that this capsule is half filled with water. Or a liquid, sorry. And it has a radius of big R. And what part 2 is asking us to do is derive an expression for the horizontal force of the spherical end cap. So we're trying to find this force. And we're going to call that f of x. And the way we're going to do that is we're going to use an integral to add up all the horizontal pressure forces acting on our spherical end cap. So we have f of x is equal to the integral dfx. Now, dfx in this case is a pressure force, and we know pressure forces are pressure times some area. So we're going to write that down, PdA. And the P in this case is going to depend on depth. So I'm going to draw a different diagram. And this is our horizontal end cap, with it being half filled with water, with our radius of r. And what we're basically doing is we're taking thin strips of our fluid and we're trying to use these as our differential area. And our pressure is going to vary with depth, like I said. So say we're trying to find the pressure at this point here. We're going to call depth h, or we're going to call this point h. And we're going to call the top of the liquid 0, or the fluid. And we're going to call this positive down h. So we're trying to find the pressure at point h, and we know that P is going to be equal to rho GH. Now what is dA going to be equal to? So dA is going to be equal to this height, which we're going to call dH. So we have dH times our width, and our width is changing as we go down. So how are we going to figure that out? If we look at this and say that this is a right triangle, or sorry, this is a right triangle here. This will be our R, and this will be our H. So our width will be equal to 2 times the square root of R squared minus H squared. So this is our width, and this is our height to get our differential area. So let's simplify this up a little bit. We can take the 2 and the row g out of the equation, have our integral still, and we have h of r squared minus h squared dh. And now we must set our limits of integration. So we know we're going from 0 to big R because our capsule is half filled with water. So from 0 to big R. And to do this integral, we're going to count our u as being r squared minus h squared, and our du as being negative 2h dh. And we can see there's a negative 2 here, negative 2, or 2 there, and then h. So we get negative rho g integral, and we need to change our limits of integration due to using u sub. So when we're at 0, we get, when h is 0, we get r squared. And when h is at r, we get 0. So these are our new limits of integration. And we get u to the 1/2 dh. So now we're going to evaluate this integral. And we know that a negative sign on the outside will flip our limits of integration. So we get rho g. Integral of u to the 1/2 is going to be 2/3 u to the 3/2 from r cubed to 0. So we get 2/3 rho g r cubed minus 0, which is just equal to 2/3 rho g r cubed. So our f of x is equal to 2/3 rho g r cubed. And that is the horizontal force on the spherical end cap of a horizontal capsule with cross-sectional radius r that is half filled with fluid.